Right, so this next video, entitled Chem 2, is all to do with non-covalent interactions. And more specifically to do with drug-protein interactions. So we saw in the last lecture about what a protein was. So in this video I want to explain how a small organic molecule, or a drug, can interact with that protein and therefore have a biological response. So if we look at this diagram, you can consider the blob in green as being a macromolecular target, and in relationship to what we did last time, let's say that that is a protein. So remember, this would be a linear chain of amino acids all folded up into secondary structure, and you would have lots of amide bonds and all of the groups sticking off the amino acid backbone to give you a variety of places or binding sites around that protein where drugs can bind. And typically there is one binding site or two binding sites for a particular protein. And because of all of the amino acids that are folded in this secondary structure, that means that at this binding site there will be certain functional groups available pointing out into space. So these groups, they could be the aromatic rings that we saw on the side chain of the amino acids, they could be the hydrophobic side chains, they could be the carbonyl or the NHs of the actual backbone itself. Any of the groups of the amino acids that we talked about last time can be positioned in that protein's binding site. The question we're looking at today is, how does a drug interact and inhibit that protein, or antagonize that receptor, or antagonize that receptor? What's going on? So one of the things you need to consider is that your drug also has functional groups around it. So you may have amines, you may have ketones, you may have ethers, you may have esters hanging off your drug. So in the drug development side of things, you optimize your drug to interact with the proteins in our body. And when you take your medication, providing that the drug can get to the site of action, there will be an equilibrium between when the drug is free in solution or in the cell, and when it's bound to the actual target. And it's this area here that we're going to be looking at today, the interaction between the drug and the macromolecular target. And depending on if you want the drug to sit in that protein binding site permanently and covalently inhibit your protein, or if you want it to be in equilibrium where it falls out and can be excreted, then it will depend on how you develop your drug. Okay, so let's zoom in to this area and see what's going on. Well, here you can see very crudely that I've highlighted the interactions with just lines, but what you'll notice is that there is a position on the drug where there is a functional group, and there is also a position on the binding site which is a complementary region to that of the drug. So if all of these are complementary to each other, they will have a positive interaction and your drug will bind. If these are opposite in their complementarity, then they will repel each other and the drug won't bind as well. So really, we're going to be looking at what is the interaction between this binding site region and this functional group on the drug. And these are your non-covalent interactions. Now obviously some functional groups cause covalent inhibition of protein, but we're not going to be talking about that today. Okay, so drug-protein interactions, non-covalent interactions. So again, just to reiterate, we're talking about proteins as drug targets here. Typically there will be enzymes or receptors. We're not going to go into drugs which bind to lipids or carbohydrates or nucleic acids or anything like that, sticking just to drug-protein interactions. Okay then, so how does a drug initiate a response? Well, it needs to, the interactions that we've just seen on the previous slide, they need to be strong enough for the drug to have an effect, but weak enough for the drug to come away once its job has been done, once its therapeutic potential has been reached. And then you can imagine that drugs with more interactions with the target will bind more for longer, and that may be something that you want to happen, or that may be something detrimental because of the half-life and the bioavailability and the excretion becomes a problem. So to enable to understand the non-covalent interactions that happen between a drug and a protein, you need to understand functional group chemistry. And if you understand functional groups, then you can understand the vast majority of organic chemistry. When these functional groups are used to bind to the protein, so the functional group here, which is used to bind to this area here, typically you may see them called a binding group, but they are essentially functional groups. It's just that their role is involved with binding. So what type of non-covalent interactions are we talking about? Well, I'm sure you've heard about all of these before, but we'll go through them in turn. So first of all, I want to look at the strongest interaction that takes place between drugs and proteins, and that is the electrostatic interaction. Often called an ionic bond, or an ionic interaction, and it happens between groups of opposite charge. So you know from your previous education that opposite charges and opposite poles of magnets attract. So for example, the north pole of a magnet will be attracted to the south pole, a plus charge will be attracted to a negative charge, and that's the basis of an electrostatic interaction. So for example, if we're looking at drug molecules, then typically we're going to be looking at a molecule or a drug which has a carboxylic acid on it, which can be deprotonated. So this is your drug, and this will interact with one of the amino acids that we saw in the last video, one of the amino acids that can be protonated on its side chain, and you will get a nice strong electrostatic interaction. Here is your protein and here is your drug. Now this side chain here is one of the R groups between the amine and the acid. It's one of the groups here. This amine, don't forget, is not this one. This one is part of the chain of your protein. So this is not this one here. This is one of your R groups. Okay, so that's one example. Another example would be the complete opposite of that, where your drug has an amine on it, which obviously under physiological conditions we're looking at it in a positive role, and again, one of the acids on your protein is the opposite. And again, this acid here is not this one, it's one of the acids in this side chain. So they are electrostatic interactions. They're very strong. They're the strongest non-covalent interaction that you'll come across. They're also non-directional, so that means if you have a positive charge here or a negative charge, then it doesn't matter where around that charge the opposite charge is, it will experience the same effect. So anywhere in a 3D sphere around that charge, there will be the same interaction. And this is because the electrostatic interaction between two charges, the strength of that interaction is dictated by Coulomb's law, which says, so this is Coulomb's law, and this says that the force of the interaction, the strength of the interaction, is directly proportional to the charge on one of the molecules multiplied by the charge on the other, so Q1 times Q2. In our case, it's a positive charge and a negative charge, divided by square of the distance apart. So R here is the distance that those two charges are apart, and so very quickly, as the distance between two charges gets bigger, the strength of that interaction falls off by a squared relationship, the inverse square law. So when you're looking at drug-protein interactions, very typically the binding site of our protein, so here the binding site, they tend to be hydrophobic because they're folded up away from water, and so that means that your positive and negative charges are not affected by water so much. So it tends to be a very strong interaction. And if there isn't an interaction between a positive and a negative charge in your drug and the protein, it's most likely going to be the most important initial interaction that your drug experiences. Okay, so that's electrostatic or ionic interactions. The next one of importance is your hydrogen bonding. And typically they occur between electron-rich atoms, or we say heteroatoms, and in drug discovery typically that will be an oxygen or a nitrogen atom, and they also occur between an electron-rich atom and an electron deficient hydrogen. And typically you find an electron deficient hydrogen on oxygen and on nitrogen. So for example, if we look at a molecule of ethanol, redrawn like that, and here you have an electron-rich oxygen atom with a hydrogen on it, so a hydrogen which is electron deficient, and you can then draw that molecule again, and if you draw the hydrogen-oxygen bond, you can say because oxygen is much more electronegative than hydrogen, it has a delta minus charge on it, and it leaves the hydrogen delta plus. Now we've just seen in the previous example that if you have a positive charge and a negative charge, there will be an interaction between them, an electrostatic interaction. Here we have a partial negative charge and a partial positive charge, so they should also interact with other molecules of ethanol in a similar way. So for example, if we draw another molecule of ethanol here we have a delta minus, here we have the delta plus, so you're going to get an interaction between the delta plus and the delta minus, and that can continue. So you'll have another ethanol molecule, so again delta minus, delta plus, and this will continue in a matrix. And this is exactly why ice. What solid water is ice and steam. It's all to do with the hydrogen bonds between water molecules, or in this case ethanol is a liquid because of this array of hydrogen bonds. In this particular case, ethanol here is acting as a donor of this hydrogen, so we say that this is a hydrogen bond donor, or HBD for short, and in this case here, this oxygen is acting as a hydrogen bond acceptor. And that's going to be important later on when we talk about Lipinski's rule of 5 in a subsequent video. So, and by the same token, this is a hydrogen bond acceptor, this ethanol molecule is a hydrogen bond donor, this oxygen is a hydrogen bond acceptor, this ethanol molecule is a hydrogen bond donor at hydrogen. So alcohols can behave as both a hydrogen bond acceptor or a hydrogen bond donor because of the lone pair of electrons on the oxygen, and it's relatively electron rich. Okay, these tend to be, or you can consider them as being, weak electrostatic interactions. Unlike before, where the electrostatic interaction was non-directional, hydrogen bonds are directional, because when you're looking at atoms with lone pairs, that lone pair resides in a specific orbital, and that orbital may be sp, sp2 or sp3 hybridized, so it will be pointing in a very specific orientation, and the strongest, or the optimum orientation between those atoms of a hydrogen bond would be 180 degrees. So for example, if we have a nitrogen here with a lone pair, you would then have an interaction with a hydrogen, and then you would have the bond to its atom and then the rest of the molecule. So here you would have delta plus, delta minus, and you would have 180 degrees between those three atoms to give you a very strong orientation, or a very strong hydrogen bond. Now obviously this relationship may not be able to happen in a protein because of the constraints of the active site and the way the molecule docks into the active site, but if it was free to rotate in any way, it would position itself so that it was about 180 degrees in direction. Typically the strength of this hydrogen bond is weaker than an electrostatic interaction. Good acceptors are electronegative and have a lone pair of electrons, so typically oxygen or nitrogen, and good donors have a very electron deficient proton. So for example, if we look at some examples of good hydrogen bond acceptors and donors, things like anions, so negative charge here, or phosphate, these negative charges would be very good hydrogen bond acceptors. Other types of hydrogen bond acceptor, maybe not quite so good or more moderate, would be the acid itself as opposed to the deprotonated form, alcohols, ethers, amines, okay, these are all moderate hydrogen bond acceptors because they have lone pairs on that electron-rich heteroatom. And then if we look at some good hydrogen bond acceptors, some good hydrogen bond donors, then you're looking at, again, things like, well, I suppose the best hydrogen bond donor would be a positively charged quaternary ammonium salt. This is a very electron deficient proton because it's next to the positively charged nitrogen. But again, things like carboxylic acids, this hydrogen is electron poor, the alcohols we saw on the previous piece of paper, again, these are all donatable hydrogen bonds, so these are hydrogen bond donors. Okay, so we've seen that we have electrostatic interactions, hydrogen bonding. The other type of interaction is the van der Waals interaction. Now this type of interaction is very weak, but if there are many of them, they can build up to become relatively strong. And typically this is a transient form of a dipole. So if you think about a drug, here we have our binding site, and here we have our drug. So here's our drug, let's say this here is our protein. As the drug approaches, at a very specific point in time, if we have a very non-polar region of our drug, the electrons in that region are not going to be perfectly symmetrical. So you may have an alkyl chain in your drug where some of the electrons are at one end and they've moved away from the other end. And as it approaches your protein, what happens is the negative charge over here repels the negative charge in your protein, so the electrons push this way, so you end up with a positive charge in your protein here, a negative charge on this end, and now you've set up this weak opposite interaction. And I said it's very weak, and you can imagine this falls off very quickly with distance, but it's a transient dipole, it's a fleeting dipole. But if there are many of them, then this can become a relatively strong interaction. And so essentially what's happening is the dipole in one molecule is inducing a dipole in another as they come close together. So that's a van der Waals interaction, and that's something that you may want to look into in more detail. A fourth one is related to that really, but these are more permanent dipoles. So we have dipole-dipole interaction and something called an ion dipole interaction. And again, this is all to do with opposite charge. All of these non-covalent interactions are all really due to opposites charges attracting each other. It may be a transient charge, or it may be a partial charge, or it may be a full charge like we've seen in the last three examples, or it may be the charges associated with dipoles and ions, but nevertheless it's some kind of opposite attraction. Okay, so let's look at dipole-dipole first. And let's take a drug which has a carbonyl in it. In this case it could be a ketone. Now you know that the oxygen is more electronegative than carbon, so there'll be a delta plus on carbon as the electrons are pulled towards that oxygen, and delta minus on oxygen. So you have this dipole where you have the arrow pointing from the plus to the minus, indicating that that is a dipole in that direction. Now dipoles like to orientate themselves opposite but parallel to each other. And so if you have a dipole on your binding site or your protein, which is say going this way, then as your drug approaches, it will orientate itself opposite and parallel. So you will end up with your drug, sorry, this is your protein here, your drug will come in and it will orientate itself like this, so that the two dipoles indicated by the arrows are parallel to each other but pointing in opposite directions. And the reason for that is because you have a delta plus at one end of the arrow and delta minus at the other end. Here, delta minus at this end, delta plus at this end. Again, this is opposite charges attracting to each other. And if the two dipoles are parallel to each other, then that interaction, that overlap, if you like, will be stronger. And then by a similar token, the iron dipole is exactly the same type of thing, but again, instead of being two dipoles, you have one of them as the iron. So if we redraw our dipole here, then you could imagine if on your protein, so again this is our protein, you may have a, in this case, so I'll redraw that as you may have a carboxylic acid pointing out as one of your R groups, and there's a delta plus, there's a delta plus and a full minus charge. You have an iron dipole interaction. Similarly, up here, you may have somewhere else in your protein's active site positively charged amine, and again, you see this interaction. So we have a number of different ways in which a drug can interact with a protein. So for example, if we look at a simple example of a drug such as paracetamol. Then if you look at the drug, you can see that you've got areas where you have electron density. So for example, you have a lone pair of electrons on oxygen which could act as a hydrogen bomb acceptor. You have a hydrogen attached to either nitrogen or oxygen which could also act as a hydrogen bomb donor, and you have areas of alkyl parts which could undergo van der Waals interaction. So if you think about the types of interactions you could have with paracetamol and a protein, well, this could very well pick up the a hydrogen bond, so that's delta minus there, delta minus delta plus, could pick up a hydrogen bond there. It could also pick up another hydrogen bond over here. Let's imagine that that's going through some kind of water molecule. There's also a hydrogen bond donor here. So in this case, you may have on your backbone an amino acid which has a lone pair of electrons. So again, you can get a hydrogen bond between this delta plus and this delta minus. You may also have other alkyl chains or other aromatic rings where you get van der Waals interactions taking place here, and similarly you can get hydrogen bonding here, hydrogen bonding here, and hydrogen bonding here. So when you begin to connect all of the parts together of your protein that can interact, you can build yourself an active site. So this backbone here is your protein. Remember, all of these groups are the R groups that we saw on our amino acids, and we've seen the major types of interaction that takes place: ionic, hydrogen bonding, van der Waals, dipole-dipole, ion dipole, the types of interactions that take place between the functional groups in a drug and the functional groups that are present in the side chains of the amino acids. So that's just a very brief overview of non-covalent interactions. There's obviously a lot more detail that I could go into, but I want to keep these videos short and give you the opportunity to go away and look up more information for yourself. But one thing to leave you with is the fact that when you have a molecule in an aqueous environment, it will be surrounded by water. Similarly, the active site of your drug may also initially be surrounded by water. So have a think, or have a look around at the literature and the internet to find out what happens when a drug and a protein interact with each other and displace that bound water. Have a look at the different energy requirements for a drug to be able to bind to its receptor binding site. And we'll leave it there for the time being.